Now, we've spoken about mass defect, and the next portion of our topic is going to be talking about radioactivity and radioactive particles. Now, the thing is, even though there is a glue holding it together, okay, which is what we call the strong force, okay? The strong force is what ultimately holds this atom together. At the same time, we have the electromagnetic force, which is trying to push all those protons apart. Now, the reason we have radioactivity is because the strong force acts at a very small radius. In fact, okay, so now that's paused over here, I want you guys to understand that the strong force only has a radius that's only just a little bit bigger than the radius of the protons themselves. So the strong force is super strong, but very, very, very tiny distances. The electromagnetic force acts at a much longer range. It's a little bit weaker, but when the atoms are further apart, it becomes a stronger force than the strong force itself. So the problem lies when we start looking at atoms. Normally, when you have a few protons coming together, the strong force easily holds those protons and neutrons together. It's not really a big deal. But when you start getting larger and larger, in fact, once you move past the size of iron itself, which has over 50 protons and 50 neutrons in there, the size of the atom itself starts to get larger than the strength of the strong force. In fact, you have these particles at the fringe now that are barely being held on. And because they're barely being held on, eventually, if they get stimulated in one way or the other, they break apart. Okay? And that's what we're going to start talking about when we talk about radioactivity. So when something is radioactive, it means that the unstable nucleus breaks down into smaller and more stable nuclei. Okay? And when I say it breaks down to smaller, more stable nuclei, it's actually going to give off a few different types of particles. Our main types that we're going to be talking about are alpha, beta, and gamma radiation. Okay? So what we understood automatically about alpha, beta, and gamma radiation by using a mass spectrometer and using a velocity selector, they quickly determined that an alpha particle has a positive charge, a beta particle has a negative charge, and the gamma particle has no charge whatsoever. In fact, I'll pause that for a moment over here. In this case, an alpha particle is made of 2 protons and 2 neutrons, which is exactly what I had mentioned before that the helium nucleus was. In fact, that's what an alpha particle is. An alpha particle is simply a helium nucleus. So let's go back to here, an alpha particle. An alpha particle is a helium nucleus, meaning you have the 2 protons, the 2 neutrons, but there are no electrons. So the charge is plus 2e, or in other words, 3.2 times 10 to the negative 19 coulombs. And if you solve for the radium and uranium breaking down, so if we're going to solve for the atomic number and mass number of radium and thorium, Just keep in mind that the alpha particle is always 4, 2. So therefore, 4 plus 222 is equal to 226. 2 plus 86 is equal to 88. So we have conservation of nucleon number, meaning the top number is going to add up to be the same on each side, and the bottom numbers will be the same on each side as well. If we're talking about uranium, uranium breaks down into 22890 thorium. Okay, so keep in mind that any sort of radiation always occurs in order to create a more stable nucleus. So if we take a look at this video clip over here and look at this uranium nucleus. Now, what's interesting though is if you took the binding energy that holds the entire nucleus together, right? Since we know that energy is pretty much mass, and we actually measure the mass of that energy, it would create a certain amount of weight. But if you took the binding energies of the smaller products, the binding energy of the uranium is much greater than the binding energy of the new nuclei, which are more stable. And in fact, that since the binding energy is less in those two nuclei, there's actually some binding energy left over. In fact, if I were to actually solve for the mass before versus the mass afterwards, the total mass before of just the uranium is greater than the mass of the two particles. I just call that mass 1 plus mass 2. Because in the end, there's some energy that's left over that's not part of those two original two new molecules. And it's that energy that gets used in a radioactive, or in a I guess, nuclear bomb, actually. And it's E equals mc squared, yes. So we actually take a look at this last question down here at the bottom. It says calculate the disintegration energy when uranium turns to thorium. So uranium, as we had just calculated above, 232, breaks down to thorium plus an alpha particle. The mass before is 232.037 U. And that's going to be greater than the two masses of these particles, which is 228.029 U plus 4.003 U. So if I added this total mass up on the right, I will find the total mass is 232.032 U. Okay? So I'm missing, there's a mass defect, there's missing energy. In this case, is equal to 0.005 U. Now, the energy has to go somewhere. And usually, the energy gets turned into the kinetic energy of the molecule itself, meaning that when that helium gets shot out, it has some sort of kinetic energy. And in fact, the energy pretty much came entirely from that missing energy over there, which is, if I do a conversion factor now, is equal to 4.655 mega eV. Okay, so that's how much kinetic energy that alpha particle could have if it took all that extra binding energy that was left over. So if I brought this back over to the whiteboard over here, okay, 4.655 mega eV is really 4.655 times 10 to the 6 electron volts. If I wanted to convert that into joules, I would see that that number is equal to 7.448 times 10 to the negative 13 joules. That's how much kinetic energy that helium nucleus would now have. And I could solve for its speed by saying that value equals to 1/2 mv squared. So to quickly finish up this lesson, let's just talk about beta decay and gamma decay. If you take a look at this animation over here, before I actually start the animation, I want you to keep an eye on this neutron over there. Okay. Right now, this is an unstable molecule, and if I let this animation run, note, wait, the neutron all of a sudden changed color as it gave off the electron. As the electron was speeding out, that neutron all of a sudden turned into a proton. That's beta decay. That a neutron actually breaks down into two particles. It breaks down into a proton and an electron. So when a beta particle is emitted, it's not lost from the outer shell. The electron actually comes out of the nucleus. Okay, so with beta decay, if you take a look at this animation over here, okay, this does a nice job. You see a neutron is really composed out of 3 quarks. We're going to talk about the quarks later on. It is an up quark, a down quark, and a down quark. So it's up, down, down. However, when the particle is emitted, okay, when it gives off the electron, I'll pause it again, one of those quarks turn into an up. So it becomes up, up, down, which is the 3 quarks that make up a proton instead. And we end up giving off an electron and a neutrino, or really in this case, an anti-neutrino. So we'll talk more about neutrinos and anti-neutrinos in a moment, but understand that because it is an electron, there is no protons or neutrons, so the mass number is automatically 0. To represent its atomic number, and the fact that it's the opposite of a proton, however, we're going to represent it with a -1. So in this case, as neutrinos themselves, over here we have our 2 neutrinos. Neutrinos are neutral, and will have no mass number or atomic number associated with them. We have carbon actually turning into nitrogen, where the mass number stays absolutely the same. It's 14 on top, because 14 plus 0 is still 14. The bottom number, however, becomes 7. So radioactive carbon actually decayed into nitrogen by giving off an electron. The second example over here is called positron decay. A positron is simply a fancy way of saying a positive electron. We will talk more about antiparticles later on, but because it is a positive electron, we represent that with a 0 and a +1. So in this case over here, when radioactive neon decays into fluorine, the top is still 19, the bottom is going to be 9. In this case, it gives off a neutrino as well, which is just a very, very, very tiny, nearly massless particle. And for gamma rays, well, a gamma particle is something very different than a alpha particle or a beta particle. So let's take a look at the animation again. Now, in this example over here for the animation, we have a very unstable molecule. In fact, it just gave off an alpha particle. That's what we just saw flying off. But after it gives off the alpha particle, the nucleus is still unstable. It's so unstable that, in fact, it gives off what you just saw was a gamma particle. Which didn't have any protons or neutrons whatsoever, which is because it's simply pure energy. Okay, so with gamma radiation, it's literally a electromagnetic wave that's being given off by the atom in order for it to become more stable. So if I come back here, a gamma particle is simply an electromagnetic wave. There will be no change in the mass number or atomic number, but the fact is, when it's being given off, there's an increase in the nucleus stability. Okay? So that covers all of the main radioactive particles.